Welcome everybody to this presentation. My name is Per Skov. I'm product manager for Sabro heat pumps. Sabro is a brand in Johnson Controls, in general where we have multiple brands. You'll also see that at our booth this year. What I'm going to talk about is high temperature heat pump, and always good to clarify from the beginning, when I say high temperature heat pump, I talk about heat pump supplying higher than 100 degrees. As we heard prior, there's different solutions for that. We're going to cover that in this presentation, but also a really relevant topic. We like to talk a lot about high temperature heat pumps, meaning above 100 degrees, but I would also address the point of high source temperature. We see a lot of the projects we have sold with high temperature heat pumps are actually being realized due to the fact that they utilize a high source temperature available in the process, which makes the solution far more competitive. So some of the market trends, just to start out, it was quickly also addressed in the prior presentation. Electrification, cleaning up the energy we use, increasing efficiency, and turn energy into smart systems. And heat pumps actually feeds into all of these. Starting with the first one, the big one, electrification, which have been stated to be critical for us to reach our target of CO2 emission reductions. In general, electrification covers replacing technologies or processes that require fossil fuels with electrical solutions instead. Could be both car to electrical car, but for this case also fossil fuel boilers replaced by heat pumps or electrical driven boilers. But with regards to electrical boilers and heat pumps, it's important to look at the increase of efficiency. Heat pumps do have the COP factor, so a significant higher efficiency than an electrical boiler, and thereby, with many operating hours, they are superior on the total cost of ownership. Moving into that and talking also about excess heat, I like to talk a lot about excess heat because they are fantastic together with heat pump. I like to state the world's largest untapped source of energy. Of course, putting in a question mark because I cannot qualify it, but we do have waste heat available everywhere. The matter of fact is that in Europe, we actually have more waste heat available than we have heating demand for buildings. The difficult part is often that the waste heat is available either at a different temperature or a different location than the actual heating demand, but that's where heat pumps fits in perfectly. So here, similar example as we just saw in the prior presentation, but at the top, this is a process with a fossil fuel driven. To the left, we have 110% input to account for an efficiency boiler of 90%, and then we get 100% process heat. For this example, we have 100% waste heat then from the process. Could argue that many processes are optimized to lower the waste heat, but for the comparison here, 100% waste heat. Then if we look at a heat pump driven process below, we recapture some of the waste heat, for this case 75%, that's put into the evaporator of the heat pump, kept inside the system. By doing that, we can significantly lower the energy input into the system. So from 110% down to 25%, thereby lowering the energy consumption is in general. Other than that, also replacing it to electrical input instead of fossil fuel feeding into the electrification. Then, of course, there needs to be a clear focus also on getting renewable sources into our electricity system. But even no matter what, we need to spend the energy we have available as best as we can, meaning get the most out of the electricity we have available. So in general, heat pumps can utilize waste heat available at many different temperatures and boost it to higher temperatures that can be utilized both inside an internal process or for district heating. To go one step further, I made this mapping with different industries, example of processes and approximate temperature range. To the left, we have excess heat. To the right, we have heat demand. And for nearly every process, there is excess heat or heat loss or waste heat, many names. But if we look at the industries, we have breweries, dairies, paper, bricks, starch, chemicals, sugar, and various different processes. So the approximate temperature range mapped out here ranges all the way from 20 degrees up to 120 degrees. And a lot of these processes are being utilized already, especially in the brewery and dairy sector. We do supply a lot of ammonia heat pumps for this, also because that the heat demand in general is in the lower range compared to some of the other processes. But then if we look further down on both brewery and dairy, but also the other one, there is a significantly higher temperature requirement in those processes. The interesting part is then also that these in general have higher waste heat available. So if you look at the temperature lift across these, it's actually fairly similar across the process. Of course, this is where heat pumps fit in perfectly. They can utilize this source or waste heat temperature that's available and then supply the high temperature. So of course, one important thing is to be able to supply the high temperature. The other important part is to be capable of utilizing the high source temperature. And that's a problem we have addressed with this new product, where we can utilize sources all the way up to 90 degrees. As another example, if the requirement is not there in the process itself, the waste heat can also be put into a heat pump and then supplied to district heating. We see in some of the older district heating grid there is requirement for above 100 degrees, 110, 120 degrees, where high temperature heat pumps fit in perfectly as well. This is also commonly done in many places across Europe, up to 90 degrees with common ammonia heat pumps. But what is possible right now with this product is actually also to do it in older district heating grid requiring higher temperature. It could also be turned the opposite way around. If there's no excess heat available, could also use the district heating as a source for the heat pump and then supply into the process itself. So as a general example, like this, district heating in 80 degrees, out in the range of 50 to 60 degrees, and then supplying heat at heating from 100 to 120 degrees. The interesting part, as I mentioned, is of course the lift. And my focus on lift is because in general it defines the COP that can be achieved, so the efficiency. So if you look at the approximate temperature range for excess heat and heat demand, then we have an average average temperature lift ranging from 30 degrees to approximately 80 degrees. The lower the lift, in general, the higher COP can be achieved by a heat pump. So the low lift, as we see here, where we have high source available, is actually where we can achieve the highest COP if we utilize the high source, even though that's also where we are to supply the highest temperature. And this is mapped out in this chart that we see here. On the y-axis, I have the COP, and on the x-axis, I have the temperature lift. At the top, I have the Lorentz COP, so it kind of takes into account both inlet and outlet on source and sink side, but it's similar to Carnot COP. The curves below are 80% Lorentz efficiency, 60% and 40%. Normally achievable COP, Lorentz COP is in the range of 40, 50, 60% with heat pumps that's available on the market right now. So if we look at cases with 35 Kelvin lift, meaning utilizing a really, really high source temperature and having a smaller lift to get to 120, 130 supply temperature, we can actually have a COP in the range of 9 to 12 if we factor in the efficiency to have a realistic COP view. If the lift is then 65 Kelvin, then it's more in the range of 3 to 5. If it's 95 Kelvin lift, then it's in the range of 2 to 3. So just to have an example of a case here, if we have cooling down from 60 to 45 degrees, which is something we've done many cases in the industry, because that's where a lot of heat pumps can operate with regards to source temperature in the range of 40, 50, 55 degrees, and then supplying heating from 100 to 120 degrees. Then the COP range would be in the range 2.8 to 3.8. If a source temperature that is available in most processes are utilized at a higher temperature, here cooling down from 90 to 75 degrees, then the COP range would be more like 5.5 to 6.5. And what impact does that have? In general, nearly doubling the COP, of course, halves the electricity consumption. Lower the electricity consumptions mean lower cost to operate. Other than that, higher source temperature is fantastic since the gas density going to the compressor in general increases, meaning that higher source temperature means we need smaller compressors or less compressors. That means increasing source temperature will lower the service cost as well. Also with regards to investment, less compressors, smaller compressors are cheaper. So for this specific case, we can actually reduce the total cost of ownership by up to 55% now when we have a product available that can utilize these really, really high source temperatures. And to back this up, we can actually also see that the last 3 projects for this have actually been with source temperatures in the range of 75 to 80 degrees, and all of them with COP above 6. The highest one with COP at 7.5. So to look at the entire overview on how we cover both supply temperature and source temperature. We do have a lot of products here, actually both ammonia, we have also hydrocarbon here, and we have ammonia water mixture. So the overview you saw prior, we nearly cover the entire map with the offering from Sapro. Hydrocarbon, ammonia water mixture, and pure ammonia. So now we can utilize sources all the way up to 90 degrees and we can supply temperatures up to 130 degrees. If we start from the bottom, product called ChillPack, an ammonia chiller, often used for chilling purpose or cooling purpose, but actually also used in some cases for heating purpose or where the heat is reused, if it's for building or in Denmark with low temperature district heating grid, it is also used to reclaim the heat as well. Moving up one step further, we have HeatPack and DualPack HPC. So that's single stage and 2-stage ammonia heat pump. We actually have this product on display at our booth, so feel free to come and see it. It's a fantastic machine. These products here can supply up to 75 degrees and utilize sources up to approximately 45 degrees. This is marked as the outlet temperature that is required to stay within the boundaries of the compressor. If you go one step further up to HeatPack and DualPack HPX, it's the same platform but a different high stage compressor where we go up to 90 degrees and the same source temperature. The next product is the green part called HiCap. That's also available in 1-stage and 2-stage application. It is for high capacity heat pumps, so that's more in the range of 4 to 9 megawatt. But here with a screw compressor, we can go even further up in source temperature, and we have seen a lot of projects with this linked to electrolyzers, big capacity available at high temperature that needs to be put into the district heating grid. If we go up one step further, high temps, so hydrocarbon heat pumps where we utilize source temperatures up to in the range of 47 degrees and supplying temperatures up to 125 degrees. And then the last one, a more complex system, but really offers a unique solution to utilize high source temperature called HiPack. So this is coming from the Norwegian company called Hybrid Energy, which is now a part of Johnson Controls under the Sapro brand. Here we can go up to 130 degrees and utilize source temperatures up to 90 degrees. We have it similar to ammonia solution available as both 2-stage solution. This is the high stage compressor. We can do single or parallel compressors on low stage depending on the capacity need. This is the smallest one we have, a single stage solution with one compressor. Then we can add more in parallel if there's a higher capacity demand. Just to feed into this, like when we started to support opportunities for this, there was a lot of opportunities that was requesting the higher temperature, but actually the first one that we sold when they became a part of the Sapro family was actually only supplying around 92 degrees or something that could be covered with ammonia. The reason why this was the winning solution was because the source temperature was so high, so we had a much, much higher COP, and due to the many operating hours, it was the superior solution with the total cost of ownership. And we see multiple projects like that in the pipeline, really capable of utilizing high source temperature. So what is the technology, just as at a glance? In general, it is a normal ammonia compression cycle and then absorption cycle mixed into it. So we have an ammonia compressor, actually a chiller compressor, only operating at 22 bars, compressing the gas from a separator tank, and then here it's being mixed with the liquid from the separator tank. So gas goes to the compressor, liquid goes to the solution pump. Solution pump lifts it to the same pressure as the discharge pressure for the compressor. They're being mixed, and then they run into the absorber or the condenser. Afterwards, to a high pressure receiver, through the expansion valve, in the evaporator desorber, back to the low pressure tank, where again, ammonia and water are being separated. So why can this utilize such high source temperature? Ammonia in general, high pressure at high temperature, water, low pressure at high temperature. Mixing the two, you get something in between. But the really unique part is that we can alter the mixture of ammonia and water. So we actually can create our own refrigerant dependent on the specific need. We can also alter the refrigerant during operation by playing around with the level in our high pressure tank. So if we have a high source temperature, we add in a stronger water mixture, meaning more water into the mixture. It lowers the operating pressure. We stay within the boundaries of the compressor. And also, since it is similar to ammonia cycle, we don't need any superheat. So there's no really high source temperature or suction temperature going to the compressor as there would be with a hydrocarbon solution. In general, we have a lot of products on display, also large 3D models, so feel free to come see them. We have both solution for high capacity heat pump, high temperature heat pumps, control solution, and also configuration tool on display. Hall 7, booth 7240. Additionally, a lot of my colleagues are doing relevant presentation both around MVR, cybersecurity with controllers, hydrocarbon from my colleagues, absorption chillers, selection tools in general. So feel free to come and hear their presentation as well. Thank you.